Hi students, in this video we are going to see about multi-vector and SIMD computers in module 4. Let us go to the topic. Vector processing principles. So we first of all we must know about the meaning of vector. Vector is a set of scalar data items, all of the same type stored in a memory. Usually we will tell vector as a set of elements. That elements are called as a scalar, and how these vector elements are going to be ordered means those are ordered to have a fixed addressing increment between the successive elements called strides. So here stride is one of the another new definition. It is nothing but a fixed addressing is given to each element of a vector. So that fixed addressings are called as a stride. And vector processor is an ensemble of hardware resources including vector registers, functional pipelinings, processing elements and register counts for performing vector operations. A vector processing occurs when arithmetic or logical operations are applied to vector. So when the vector processing will be performed when it goes to the arithmetic or logical operations. And these vector processors can be increased in its speed to 10 to 20 compared with the scalar vector processing. And this topic we are going to see about these four subtopics. First one is vector processing principles, second one is compound vector operations, third one is vector loops and chaining, fourth one will be the vector SIMD computer implementation models. First one is vector instruction. How the vector instruction will be looking means there are some types of vector instructions are followed. First one is vector to vector instruction. Second one is vector scalar instruction. Third one is vector memory instruction. And fourth one is vector reduction instruction. Fifth one is gather and scatter instruction. Sixth one is masking instruction. Vector to vector instruction. Here both the operands are vector. Those are fetched from the respective vector registers and entered through a functional pipelining unit. Okay, here both the operands are considered as vector. Those operands are fetched from a respective vector registers, and after it is fetched, it is going to be entered into the functional pipelining unit. And second one is vector scalar instruction. Here one operand is vector, another one operand is scalar. I'll show the types of instructions. Here vector to vector instruction. This F1 is the first example for vector to vector instruction. Here the data from VA is moved to VJ, and second one is VI multiplied with VJ is moved to VK. So here arithmetic operations also involved and store and forward in store operations also forwarded in vector to vector instruction. Here VI is one operand, it is considered as vector, and VJ is also another operand considered as vector. The second type is vector scalar instruction. Here F3, that mapping is called as F3. Here one operand is vector, another operand is scalar. So say for example 6 plus V1 is added and it is stored in the register of V2. Okay, so this is the second type. And third type is vector memory instruction. Vector memory, whenever the memory instruction involves, it consists of either load operation or store operation. Here the value of the vectors should be stored either stored in vector register or should be loaded in vector registers. Then fourth one is vector reduction instruction. So these instructions involves the concept of maximizing the value, minimizing the value, sum, mean value, and finding the average. And gather and scatter instruction, it involves used to gather or scatter vector information randomly through the memory. So it uses these sparse vectors. And masking is also another type of instruction. It used to compress or expand a vector to its indexed vector value. Okay, so these are the 6 different types of vector instructions available in this thing, and before going to process each one, we must know the principles behind the vector processing. What is meant by vector, and what is meant by stride, what is meant by vector processor, and what is the process of vectorizing. So these things we must know. So first of all, we see what is meant by vector. Vector is an ordered set of scalar data items, right? Then stride is nothing but fixed addressing increment between the successive elements. And vector processor, it is an ensemble of hardware resources. Vector processing unit performs either arithmetic or logical processing. And vectorization is the one of the process. It involves the conversion of scalar data into vector data. And one more compiler is there. That compiler is called as the vectorization compiler or vectorizer, and it is capable of vectorizing. If a compiler is capable of vectorizing, means that compiler is called as a vectorizer. And types of instruction. And apart from this vector instruction, there are some access memory schemes are followed in vector processing. What are those means? Those are coming under the 3 types of categories. We'll see before how this access memories are involved in vector. So when you take one vector operands, it has the arbitrary length. So the length of vector operand is defined as arbitrary, and vector elements are not necessarily stored in a continuous memory location. So there is one condition that vector elements are not necessary to be stored in a continuous memory location. And to access the vector memory, one must specify base, stride, and length in order to access a one vector into the memory. So these 3 things should be specified. And since each vector has its fixed length, one segment of vector can be loaded into a vector register. So because of every vector has a fixed length, one segmenter can be loaded into the registers. So based on the vector operands, this vector memory organization is divided into 3 types. One is C-axis memory organization, second one is S-axis memory organization, and third one is C-bar S-axis memory organization. This is nothing but, C is nothing but concurrent. So concurrent access means parallelly. Parallelly, if the memory is going to be accessed, means concurrently, means that kind of organization and that kind of memory access is called as C-axis. And sequentially if it is going to be accessed, means those kind of access memory is called as X-axis. So the combination of these two is called as S and S-bar X access memory organization. Here how the memory should be organized, mean it should be organized in a interleaved manner. We have studied the interleaving concepts in the module 3. So here what is the interleaving technology they have used, means low order interleaving. So we'll see the instructions types in detail with diagram. Here vector to vector instruction. Here vector to vector instruction both consist of 2 operands as vectors. So here Vj register is the one operand, Vk register is the one operand. So this is going to be involved in a functional unit. Whatever the performance it's going to be performed will be done in a functional unit. After its completion of its work, it is given to the output register, that is nothing but Vi. So this is what happening in the vector to vector registration instruction. But in vector to scalar, here in order to maintain the scalar data, one scalar register is there, like the same as vector register. Here one operand is from vector register, second operand is from scalar data. It is given to the functional unit. After its completion of the work, it is given as output to the another one vector register. So this is very easier one. And vector to memory instruction. Memory means there is a centralized memory is accessed. So for load operation and store operation, the memory vector path should be maintained. That is vector path in the sense memory path should be maintained. Here this first operand shows the vector load. That means the data from memory is loaded into vector register and it is given to the output register. And second operation is called as a store operation. So data from vector register is stored in the memory. So likewise it is vector to memory instruction is done here. Then these two are the vector to vector instruction is one type of instruction, and vector to scalar and vector to memory. How it happens means vector load and vector store are the two basic examples of vector to memory instruction. And fourth type is vector reduction. Reduction in the sense it reduces, minimizes and maximizes its vector value. Here this vector value is reduced to, here the vector value is reduced to scalar. The next type of instruction is gather and scatter. What happens in gather and scatter means the memory value from memory is gathered into the two vector registers Vi and Vj. And scatter, what happens in scatter means the two scattered vector registers values are multiplied and it is loaded into the memory. And then another type of instruction is masking. Masking, here in this example V and Vm is multiplied and it is stored in the Vj, but here the second operand Vm is considered as binary vector. And let us see the architectural, that means the example of each instructions here. So first instruction is gather instruction. Gather, what happens here? V0 register and V1 register. V0 register has some values, V1 register has some value. But V1 register is mapped with the memory. So how it is mapped means this value of 600 is mapped with the 104 address and 400 is mapped with the 102 address. Likewise, these elements, these data are mapped. So here in gather, what happens? These two registers are multiplying the values of a VL register is stored in the A of 0. So here A of 100. Here 100 is the memory address and value 4 is stored here. So this is what happened in the gather. And scatters, it is an opposite of scatter. And what happens in the masking? Masking, here VM register is termed as the binary registers. So here binary register is tested in the VIVO register. This VIVO register is a tested register. Then each bits are represented with the V1 register as a result. Then coming to this one, vector scalar performance. How we can relate the vector performance with scalar performance means there are some formulas are given. Vector scalar speed of ratio R and vectorization ratio in program is represented as F. So what happens? The relative performance is represented as P. It is given with the formula of P is equal to R divided by 1 minus F into R plus F. So what happens here? It is indirectly proportional with the factor of F. So when the factor of value of F is low, when the value of F is low, so the speed up will not, we cannot achieve the speed up. So it will be again termed as low. So that's what value of F is low, the speed up will not be achieved more. And what is the limiting case means? That is the minimum case means if P is equal to 1, F is also turns to 0. And maximum case if P is equal to R, that is the maximum case, at that time F will be turned into 1. The next topic is compound vector processing. Compound vector processing is nothing but a composite of vector operations converted from looping structure of linked scalar operations. So here this is the example for compound vector processing. For it starts from the for I equal to 1 to n. So from whatever the value from I to n, this repeated operations will be carried out. So what are the operations involved means load operations, store, again loading of two vector registers and multiply, add, again store. So this is the end of loop. This combination of instructions are called as compound vector functioning. So here are some of the examples of compound vector functioning examples. Here V2 of I plus V2 of V of 3 into V of 4 is a one composite function. It carries addition operation and also multiple operation. After its operations are done, it is going to be stored in the another one vector register. Like that, this is the combinations of more than one vector functions. And what about vector loop? Vector loop should be carried out in a stripe mining approach. Okay, it is carried out in the stripe mining approach. And what vector chaining is done in the example. In the example, it is given as SAXPY code code, it is limited chaining using only memory access pipe in Cray1. Cray1 is one of the example. Cray XM underscore MP is another example. Here in Cray1 architecture, it is done in a one memory cycle pipe. I will show how it is done. So I will show here Cray1. This is the sequential execution, and this is the pipeline execution with three memory pipes. See, I'll show. First, we will go for the example here. So, what happens in the this compound vector function? You listen load of R1, R2, R1 load of R2, multiply, add, and store. So, what happens? It is if it is executed using a single memory pipe means first load operation will be carried out. It takes some sequential time. After the completion of this first sequential, it goes to the second load operation. Second load operation is done, and after that only it is multiplication. Multiply pipe will be used, adder pipe will be used. After the execution of this multiply and adder, it is going to be stored in the another one memory. So using memory pipe. So this is the chaining of arithmetic pipes using a single memory pipe. But in Cray X underscore MP architecture, it is done in a pipeline fashion using three memory pipes. So here load and X can be done simultaneously because it uses threes. So a simultaneous execution is allowed. Similarly, store Y is also another one pipeline, another one memory pipe. It can be executed in simultaneously. So when you compare the time taken in a single memory pipe with the three memory pipe, in the second type it is reduced. So you can observe the lesser number of time taken in a third memory pipe, three memory pipe architecture. I hope you understand this concept. I will catch you in the next video about next topic. Thank you.